Good morning, good afternoon, and good evening, everybody. Thank you for joining our webinar today. Our host is Mark Thomas, the Systems Engineer on the Cambium development team. And today we will be discussing dynamic spectrum optimization in the PTP 650, 670, and 700 products. We're going to wait a couple more minutes to see if we have any more joiners, and we will get started with Mark. Okay, we'll go ahead and get started. Mark Thomas is the Systems Engineer for the Cambium development team. Thank you everybody for joining today. Our webinar is on dynamic spectrum optimization. Hi Mark.
Hello, can you hear me?
Yes, I can.
Well, that's excellent. I'm Mark, I'm your presenter for this session. Dynamic spectrum optimization, not as easy to say as Susie thought. I have worked for Cambium for 12 years, a little bit more, and in a lot of that time I've worked on the PTP 300, 500, 600, 650, 670, 700, 800 products. And one of the characteristic or signature features in the products for the unlicensed spectrum is dynamic spectrum optimization, and that's what we're going to look at today. If I could advance the slide, that would be great. Anybody who's built a point-to-point link in unlicensed spectrum will have encountered RF interference. To some extent, it's the bane of our life. I was looking at some measurements done between two oil platforms in the North Sea recently, and it was remarkable. It's a completely quiet RF environment. If only every city and location was like that, building radio systems would be easy. But sadly, it's not. We've got a lot of advantages in having unlicensed or shared spectrum, but it does bring a few challenges with it. And the main one is the unpredictable nature of the RF interference. And this arises when other operators build new systems, which they're allowed to do, and it's a pain to us, or they re-engineer or optimize or change their frequency plans. That cause our links a problem. Nomadic users who move into the area and maybe electronic news gathering or some event or something like that. Seasonal changes can affect us because leaves on trees attenuate at 5 gigahertz quite well, and bare trees are much less so. So summer to winter can shield us from interference. And then there are primary users in many of these bands, systems like weather radars that we call the TDWR. Sometimes we have to cope with those. Some people operate their links in shared spectrum on a fixed frequency, and if you were doing that, it would be a great idea to do a spectrum scan and choose a quiet channel before deploying the link. But even then, you might pick a really good channel when you put the link in, but over time the interference environment can change, and what was a good channel will steadily degrade, and the quality of service you're offering to users is going downhill. Monitoring and responding to this changing interference environment is one of the big challenges we have, and we think the features we've given you in PTP 650, 670, and 700 are the best there is for surviving in this challenging environment. DSO, what does it do? It gives the ODU the ability to pick a channel at the master end of the link before at the master before establishing a link. Then to conduct a continual background scan while the link is working to find channels with the lowest interference level, to coordinate between the two ends of the link to make a channel selection and move to the preferred channel, and a way to make that change without dropping the link, and in many cases without dropping packets. So that's the function that allows the radios to dynamically change channel responding to the interference conditions. But in addition to that, we have a pretty functional Spectrum Expert page in the web interface, and this is providing a spectrum view through which you can understand the logic of the channel change decisions that have been made, and allows you to analyze and view historical data to understand a lot more about the interference environment that you're working in, and a few controls to tailor or configure the DSO feature. Susie, can you move the slide on, or
I don't have access to your screen. It's not advancing with the arrow, or
it's a bit temperamental. I'm not sure why that was.
Sorry about that.
No, well, we were technology. We all struggle with it.
It is a new system, so our apologies, everyone. We're still adjusting.
Yeah, we do understand some technology, just not WebEx.
Exactly.
So on this slide, we can tear down the DSO feature into some sort of component functions, and we're gonna look at these in some more detail. So I guess we don't need to dwell too long on this one. We're going to break down and look at how we make measurements of the spectrum, how we analyze the samples, how we display what the channel change algorithm is, what happens to the modulation mode, how we deal with channels that are barred by regulations or channels that we barred because we don't want to use them, and what happens with bands that have enforced radar detection. cool feature we've got called the extended spectrum scan, and for people who really want to understand what's happening in their band, a waterfall pane and a time series pane. So this is a slide about actually making the measurement that the DSO feature is based on. These radios always use time division duplex, and I guess most people know what that is. It describes the fact that in these radios, one end of the link can transmit or receive, but it can't do both at the same time. Products in licensed microwave tend to transmit on one frequency continually and receive on another frequency continually. But a better approach in shared spectrum is time division duplex, meaning for half the time the master transmits and the slave receives, and for the other half of the time the slave transmits and the master receives. And in these PTP products, the transmit and receive, it alternates in a fixed duration cycle. Now, when I say fixed duration, the actual period of the TDD frame depends on how you configure the link, and the bandwidth, link range, the link optimization, and the link symmetry all affect the calculation of the period. In most links, there's periods between about 1 millisecond and 5 milliseconds. Shorter periods give you better latency but worse efficiency. Longer periods, better efficiency and somewhat worse latency. So I said half the time we're transmitting and half the time we're receiving. That's not quite true, because sandwiched in the middle there's a short spectrum measurement interval for DSO. And we've put that at a time in the frame when the ODU isn't transmitting or receiving. It's like a dead time in the TDD frame. And it's quite important that the DSO measurement is done in dead time, because it means we're not measuring the wanted signal either transmitted or received in the link. If we're going to compare the channel that we're on with an alternative channel, it's important to measure the two on the same basis. So you'll see in the spectrum display, we can display the noise level in the channel that we're operating in. And of course, that's something you could only possibly do with time division duplex. It also means that if you have a synchronized network, this measurement is in a period when no links are transmitting. So DSO doesn't see the other links synchronized to our link in a synchronized network. Right, so we've got this short measurement opportunity in each TDD frame, and what the radio does, it tunes to a different channel each time it makes a measurement. So it cycles through the available channels, perhaps starting in the lowest channel and moving up one channel in each TDD frame until it's measured all channels, and then repeats from the bottom of the band. That means the time between making measurements on a particular channel depends on the frame period, so how often we get to make a measurement, and the number of channels, meaning the number of measurements we have to do before we come back to the channel we started on. So that all the DSO feature is based on processing the measurements made in this DSO measurement period. one sample, one measurement is the average power in a 6 microsecond period. It seems like a pretty short period, and we don't want it to be too long because we don't want to waste the capacity in the TDD frame. But it turns out in practice that you get a very good view of the interference in a channel by sampling it with a period even as short as 6 microseconds. We can do a little example on the rate of measuring an individual channel. If we're in 5.8 gigahertz and 30 megahertz bandwidth with the IP optimization, we have a 4.4 millisecond TDD period. We have 10 channels available, so it's going to be 44 milliseconds by the time we come back to measure on the same channel. Bands with more channels are going to take longer to come back to where we started. So the ODU has this has a continual input of samples, like, say every 4.4 milliseconds in my example here, and we have to try and process those to learn something useful from it. And what we do is we collect the statistics in a rolling 20-minute window. So that means we collect the samples for 20 minutes, and then when we've got 20 minutes of data, it's a 1 in, 1 out. So for every new sample that contemporary sample we add, a 20-minute old sample is discarded. We sort the samples by channel, and then in each channel we produce 3 statistics. The peak is the biggest measurement in the 20-minute window, full stop, just the biggest measurement. The 99.9%, that's like the 99.9th percentile, that's a level that's exceeded by only 0.1% of samples. In the example we had above, you would get about 27,000 measurements in the 20-minute window. So the 99.9% is a level that's exceeded by about 27 samples out of the 20 minutes. And then the mean is simply the average of all the samples on a particular channel. Then we take that data and we display it. And okay, I guess after 12 years working on the same product, I'm quite attached to this display, and it tells us quite a lot about how the radio is working and about the band that we're working in. Right, I had to think what order are we going to look at this? Yeah, if we look top left, there's a call out that says green bar, the bandwidth of the active channel. In this example, the active channel, in this example, the radio is configured with a 20 megahertz channel bandwidth, and that's shown by this light green shaded area. And at the bottom of that green shaded area, there's a darker green square. That's the active channel. That's the channel that we're operating on, and you can see that's a 5490 megahertz, 5490 megahertz. That's the channel that's been selected by DSO. The little spectrum analyzer display, this is in channels in 5 megahertz increments. The reason we are showing that is those are all the channels that are available for selection. Even though the channel bandwidth of the radio is 20 megahertz, the channels that we can pick from are on a 5 megahertz raster. I haven't put this in the slides, it's just occurred to me, it's a really important point, that the bandwidth of the measurement is the same as the bandwidth of the link, in this case 20 megahertz. We've made the measurement with a 20 megahertz wide filter, so the data in that green active channel, that represents the interference level in our operating channel, in the entirety of our operating channel. So we display in these sort of vertical bars, and it's quite interesting to look at the vertical bars. The top of the colored rectangle, that represents the 99.9% measurement that I was talking about in the previous slide. The vast majority of samples fall within the colored rectangle for each channel, and then superimposed on that there's a sort of an eye-shaped beam. At the top of that beam represents the peak, the single biggest sample, and the bottom of that beam represents the average for the channel. What you can see is the channel at 5565, that has a big I-beam sticking out the top of it. It goes up quite high. That's telling us that channel has got a very peaky interferer in it. The average level is, I probably should have mentioned the left-hand side of the screen is a power scale in dBm. So if we look at that 5565 data, the average is at about -80. Nearly all the samples are below -78, but we have a peak at -50. Generally speaking, if that channel stays like that, it might be a good one to avoid, because those peaks are very hard to mitigate against, and they're unexpected, and that's a bad choice of channel. And then we should point out there is a color code. The blue ones show interference level below a threshold. I think the threshold here was set at -85. The orange ones represent higher interference levels, and you can see that the orange is slightly intensified in the channels with the greater interference. So the idea of this whole display is you would look at it and you would see the green rectangle 5490. That's where we're operating. It's got no peak interference problem. The interference level is the lowest, or the sort of equal lowest across the channel. So we look at that and say that's about as good a choice as we're going to make in this band. This slide is about the algorithm that we use for making a decision to change the channel. The spectrum that we just looked at there would be no need to change it. It's about as good as it's going to get. But if the situation changes, then the ODU prefers the channel with the lowest 99.9 percentile measurement. So in the previous slide, that would be the top of the colored rectangle. And the ODU organizes the channel change when the preferred channel is better than the operating channel by more than a certain amount. And that default amount is 3 dBs. If it was a lot more than, if you set the threshold more than that, you might pass up on the chance of a better channel. And if you set it smaller, then you might be changing for no good reason. There's also a hopping period control, and you can see the margin and the period inside the red rectangle on this slide. The meaning of the hopping period is that having made a change, there's no further change in this period. And if you're looking for these controls in the web interface, they're only at the master ODU and they're not on the slave ODU. You configure them once at the master, and that suffices for both master and slave. We do have an option for asymmetric and symmetric DSO, and slightly cryptic name. I'm not sure I invented this name. Symmetric DSO, the master ODU picks the best channel for master to slave direction and slave to master. It's combining the measurements of the two directions to make what is overall the best or least worst decision. And in asymmetric DSO, the two directions are uncoupled, and the master to slave channel is chosen independently from the slave to master. That might be a good strategy in a very heavily interfered band, where you can see a good channel for one direction and a different channel that's good in the opposite direction. The disadvantage generally of the asymmetric approach is that the spectral efficiency is halved because you're occupying two channels but only sending the same amount of data. We've got an option for a real-time display, and this is a screenshot here with the grey, snaky Loch Ness Monster sort of line that's added. This displays the very latest samples that have been measured in DSO, and it's updated every 2 seconds, and that can be handy if you are experimenting or trying to screen interference or to align, because it responds instantly as opposed to the rest of the measurements here, which are the result of statistics in the 20-minute window. So the rest of the display is a rolling 20-minute window. The grey snake is a instant measurement updated every 2 seconds. Now you might have a good reason for not wanting to use a channel. And so what we have here is an opportunity to bar channels. The DSO won't select a channel that's barred. And the reason that you might bar a channel is if you know it has an interferer in it, but the interferer is sporadic. Perhaps it's during office hours or something like that. And you don't want to move to that channel knowing that you're only going to have to move again. But there may be periods when, to DSO, it looks like a good one. So this little yellow padlock symbol indicates that these are channels we don't want to use. And those have been set with the button that you see in the display bar channels and the partner button activate channels, which is the opposite way round. If you bar the channel that is active, DSO will kick in instantly and move to the best of the rest, whatever channel was better than the barred ones. These displays here I captured this morning. We have a trial network where we operate most of the Cambium radio products, and we have line of sight links and non-line of sight links, point to point and point to multi-point, at a variety of simple and challenging conditions. So I logged on to a link that's in our trial network. These screenshots came from earlier today, except for this one, which came out of the user guide. Sometimes channels are not available for use because the regulations say we can't use them. In that case, you have no option to use them. It's a function of the regulatory band, and they're displayed in black with this red sign, which certainly in the UK is a no entry sign. I'm not sure if that is so in the highway code of every country. Okay, so here is one of the coolest features, in my humble opinion, the extended scan. To operate the extended scan, you have to set extended spectrum scanning to enabled. If you look at the red box on the slide, that makes the DSO measurement, instead of cycling through the channels in the regulatory band that's been configured for the radio, it cycles through all the channels in the coverage of the radio. And for a 670, that's from 4.9 gigahertz to 6.05 gigahertz. That's an awful lot of channels. And in the display here, those channels are at 5 megahertz increments, so it makes for quite a busy display. The grey ones are the ones outside the 5.4 band where this link is operating. And you can see in our trials network, certainly from 4.9 up to 5.4 is very quiet. That would be super spectrum, and I think most people would be really happy to use that. And then in the 5.8 band, there is certainly one fairly high power link already working there. So I mentioned you have to set extended spectrum scanning to enabled. That makes the DSO measure all the channels. And then the other control, display mode, when you set it to extended, it displays all the channels. If you untick extended, then you're only looking at the operating band, same as we saw in the other slides. But the radio is still measuring all the channels. So I would suggest this this extended scan is brilliant if you're struggling with the link and you think, I wonder if other bands are available and they might be better. So that makes for a great survey tool and a great decision aid. Should I use a different band? Should I go from 5.4 or 5.8 or whatever's available? But having done that, I suggest disable the extended spectrum scan, because the time it takes to go through all the channels is extended because there's a lot more channels. So once you've picked a band, disable it, and then DSO will work better because it cycles through the actual available channels much more quickly. This is a useful display that we have on the Spectrum Expert page. You display the bit at the bottom. The bit at the top is what we've already been looking at, and you'll see that I barred some channels, and so the active channel has gone up to 5.520. There's nothing wrong with the ones below, but I barred it to take a screenshot, and now it's moved up there. The bit at the bottom of the display is what you get when you click on a local interference waterfall. It expands the pane, and then you click it again, and it hides it, shrinks it. The key to the horizontal axis of this is the same frequency axis as the spectrum. The vertical axis of the waterfall is time, and it's a non-linear time because you'll see it at the top of the display is now, and then you've got 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes, and an hour, and that's on one scale. And then there's another 24 hours below that at a more compressed scale. Why this is a good display is it can show you trends over 24 hours. And that may help you to select channels that are going to be good all the time, as opposed to good of a short period when you if you just look in a 20-minute period. And what we can see here is there is some other system operating between 5.540 and 5.600, and that's been operating all the time. And then we just had a little bit of interference on the channels at the bottom at about 6 hours ago and at about 20 hours ago. The right angles and circles element on the left, that shows the history of the operating channel. That shows where I barred channels and forced it to pick a new one. That's a great display because you can tell if DSO has been making rapid and frequent changes, or if it's picked a good channel and stuck with it. And if that's not enough information for somebody, we also have this time series display. The time series is an amplitude trace for a single channel. And in this case, we've selected 5560 as the frequency. We selected that in the spectrum display and turned on this time series. Now the now point is at the right hand side of the display, and the first section, going from right to left, you've got an hour in excruciating detail and a 24 hours in less detail. The three traces in the time series, we have the red one, which is the peak, same definition of peak as we had before. The blue is the 99.9 percentile, and the black is the mean. The display changes a little bit here. When we go from right to left, we get the first hour at one resolution, and then samples a consolidated, and that accounts for the different characteristic of what we see on the left of the display. If you look on the right of the display at point about 10 minutes ago, we have a peak at about minus 53, something like that, minus 53 dBm, a single peak. And that corresponds to the top of the I-beam on the spectrum display. That's the sample that has set the I-beam, and here it is. You can see the point in time where it occurred. Now, I don't know what this interferer is, but for some reason it lights us up periodically with quite a big signal. And finally, on this display, you'll see that the right-hand 20 minutes is white, and the rest of it is got a shaded background, and that's to remind us that the spectrum display and the DSO decisions are based on the last 20 minutes, and that's the white portion at the right-hand side. If I said finally, that's because I forgot there was one more slide. If we're in a band with DFS or radar detection, when radar, whether it's either the FCC approach or the ETSI approach, if we detect radar on a channel, that channel becomes unavailable for 30 minutes before we can go back. And if that's occurred, we can see it in this display here, because the channel is colored red. Red is a channel that's temporarily unavailable because it's been a frequency where a radar detection took place. And that, I'm sorry to say, is all I've got to say about DSO.
Thanks, Mark. We do have a couple of questions. I will read them to you in the order that
I'd be disappointed if there weren't.
All right. The first one, what is the delay for ODUs to switch channels?
Okay, that's an interesting. There's a couple of different ways. There's three ways to answer that question. If we mean when the interference degrades, how long will it take for the system to respond? then we would say, remember that the decision is based on the 99th percentile. And that's calculated in a rolling 20-minute window. So that does imply a certain damped response, because a sudden increase in interference won't show through to the decision-making process until we've got at least a fair bit of the 20-minute window full of the larger samples. So that's one answer, is if it's a modest increase, it will get round to changing. A second way to answer it is, I haven't described this aspect today, but there is a escalated channel change when the interference level increases suddenly, and in that case, an abrupt and significant increase of interference on a channel results in an immediate channel change without any delay at all. So that's kind of emergency change. The third way of answering it is what happens once we have taken the decision to change channels. Once the decision is made, we've got about 10 TDD frames before the frequency changes, and that's because we need to coordinate the change at the two ends of the link. And it's actually quite a sort of simple mechanism where they count down the TDD frames until the channel change, and then both ends of the link hop to the new frequency in the same frame. And it's probably worth saying, having arrived, so that we've got about a 10 frame delay before making the change. We haven't got any frames lost in making the change, because it's coordinated at both ends of the link. However, we don't have any channel state information for the new channel. And so the only safe thing to do is to start again at BPSK modulation mode in the new channel. And this is why you don't want to be changing channels all the time. So we'd start at BPSK, and if the channel supports a higher modulation mode, we'd expect to ramp up over the next couple of seconds to get to 64 gram or 256 gram or whatever modulation mode is possible. So the drawback of that is that the capacity of the link drops when we're in BPSK. If you're using quality service, then high priority traffic will still get through, but the lowest priority traffic may be buffered for a few TDD frames whilst the modulation mode climbs again. And that might be seen as a quality service glitch for users who don't have high priority traffic. So there's three answers there. I hope one of the three is the answer to the question.
The next question is, if the system is automatically looking for a clear channel, could it get stuck in a bouncing type effect by constantly changing channels, or is there a timer to prevent too many changes in a noisy environment?
We've got the hopping period control, which defaults to 180 seconds, and that's telling us that having made a change, we won't make another change until that period has elapsed. So that's our protection against bouncing around all the time, and also the hopping margin, defaulting to 3 dBs. If you thought it was hopping too much, you would increase that so that only changes, more valuable changes, would be followed. The emergency change, that's not subject to the 180-second lockout period. But if you had interference that was triggering this emergency channel change all the time, probably should be looking at different band.
Okay. Ready for the next question?
Oh, yes.
Okay. How the CH hopping works in a hub configuration of more than 2 links? That was the question.
Okay. If what we're thinking is like a hub configuration of point-to-point links where you've got a tower and maybe the master end of each link is on the tower, but the slave end is on some other building or some other site, then if those links are synchronized with TDD synchronization, one link won't see the other links as interference because the measurement period occurs in the dead time in its own link and in the dead time in the other links in the hub. So if it's a hub and spoke of synchronized links, then the links will be blind to interference from their neighbors, and if that's likely to be a problem, it would be a good idea to use the channel barring and give each link a non-overlapping choice of channels. You could, if you say you had 3 links, you could carve up the channels into 3 groups and bar 2/3 of the channels for each link, so that each one has a limited choice and ensuring that it doesn't overlap with one of the other ones. If it's a hub and spoke and you have somehow managed to make the links work with enough frequency or space separation on the tower to work without synchronization, then the links will see, each link will see the other links as interference and will take DSO decisions to avoid the other links on the tower.
Okay, thanks, Mark. That was the last question that we had. Thank you, everybody, for joining us today. This will be posted to the community and our YouTube page along with the slides. I did see that some of our attendees did have some audio issues. Sorry about that. Again, this is a new system. We're still adjusting, and we will certainly look into that. Thanks, Mark, for your time today, and that will be all.
Thank you very much, everybody, for listening.
Thank you. Have a good day.